Welcome to this tutorial on model-based design for quadcopter autopilot, from concept to prototype. Here is the outline of this tutorial. In this session, we will explore system-level requirement validation and demonstrate how to leverage simulation for model-based validation of requirements. What is requirements validation? Here is a definition from a guideline for civil aircraft and systems development. Requirements validation is the process of ensuring that requirements are correct, complete, consistent, unambiguous, verifiable, feasible, and traceable. Requirements validation ensures that the right system is being built before development progresses too far. Validating requirements is essential because errors made during the early stages, such as in requirements or design, can lead to costly and time-consuming rework if discovered later. These errors often stem from misunderstandings, incomplete requirements, or miscommunication among stakeholders. Traditional development methods tend to detect such issues during implementation or testing, when changes are harder and more expensive to make. Fixing a requirement flaw at that stage can ripple through the system, causing delays and increased costs. Model-based design addresses this challenge by enabling early validation of requirements through simulation, formal verification, and rapid prototyping. This shift-left approach helps catch issues sooner, reducing the risk of late-stage failures and improving development efficiency. This table lists several examples of system-level requirements typically found in drone development. Hover time, waypoint accuracy, emergency landing, maximum altitude, and operating temperature. These requirements are often subject to validation through simulation, prototyping, or formal analysis to ensure they are feasible, verifiable, and aligned with stakeholder needs. In this session, we'll take hover time as a case study to demonstrate how simulation can be used for effective requirement validation. Let's formalize the hover time requirement. The quadcopter shall be capable of maintaining a stable hover for a minimum duration of 20 minutes under nominal operating conditions. The hover time of a drone depends on several components, including the battery, motor, propeller, electronic speed controller, payload, mass properties, and environmental conditions. More specifically, the key configurations of each component that can affect hover time are listed here. These components and their key configurations can be modeled and simulated. For detailed information and demonstrations of these models, please refer to the previous sessions in this tutorial. The models and simulations enable us to perform model-based requirements validation effectively. Now, let's head over to Simulink for a demonstration. To begin the demonstration, let's open the battery model. The battery cell capacity is set to 0.5 ampere hours. We'll now run a simulation where the drone maintains a hover until the state of charge, SOC, of the battery reaches 0. From the simulation results, we can observe that the hover time for the current configuration is approximately 782 seconds. In this case, the hover time is less than the required 20 minutes. This indicates that the current configuration does not meet the requirement. To address this, we have two options. First, adjust the requirement to reduce the minimum hover time, or modify the drone's configurations, such as increasing battery capacity or improving propulsion efficiency. With models and simulations, we can explore and evaluate these design iterations efficiently, enabling early validation and informed decision-making. This diagram highlights some of the configurations we can adjust to improve hover time, such as battery capacity, motor efficiency, propeller size, and overall payload. This table provides more detailed insights into how each component's configuration affects hover time, along with possible optimization strategies to improve performance. Please take a moment to pause and review the table. Now, let's return to the battery model in Simscape. This time, we increase the battery cell capacity from 0.5 ampere-hours to 1 ampere-hours. Since higher capacity typically means more weight, we also increase the battery mass by 0.3 kilogram to reflect this change. We'll run the simulation again, where the drone hovers until the battery's state of charge, SOC, reaches 0. From the simulation results, we observe that the hover time is now approximately 754 seconds, which is actually less than the previous result of 782 seconds. This figure shows the flight time as a function of battery capacity. As illustrated, flight time does not increase linearly with battery capacity. Instead, it follows a nonlinear trend, reaching a peak where the energy added by increasing capacity is balanced by the additional weight. This peak represents the optimal battery configuration for maximizing hover time. While optimizing for hover time is important, it's equally crucial to balance other system-level requirements. Factors such as maneuverability, wind tolerance, payload capacity, and thermal or electrical constraints must also be considered. Improving one aspect, like flight time, can sometimes negatively impact others. Therefore, a holistic system-level approach is essential to ensure the drone meets all performance, safety, and operational requirements. Here is another example configuration, this time optimized for maneuverability. To be more specific, hover time is influenced by multiple subsystems: electrical, mechanical, aerodynamic, and environmental. Optimizing it requires careful balancing of trade-offs across disciplines. For example, increasing battery capacity may extend hover time but adds weight, which in turn increases power consumption. Larger propellers can improve efficiency, but may reduce maneuverability and increase structural demands. Reducing payload improves flight time, but may compromise mission objectives. Motor and ESC selection affects both energy efficiency and thermal constraints. By using simulation-based, model-driven design, engineers can virtually evaluate these cross-domain interactions, explore how different subsystems interact, such as propulsion, power, structure, and environment, before building any hardware. Ultimately, it helps teams design better performing, more robust systems while reducing development time and cost. Designing drones involves trade-offs across multiple disciplines: mechanical, electrical, software, aerodynamics, and control systems. Managing this complexity requires a systems engineering approach. Systems engineering enables teams to capture and manage requirements across domains, define system architecture that reflects functional and physical structure, establish a verification and validation workflow to ensure the system meets its requirements, conduct safety and reliability analyses, critical for regulatory compliance and mission assurance. Apply model-based design, MBD, to simulate, analyze, and validate behavior before hardware exists. This structured methodology helps ensure that multidisciplinary decisions are traceable, testable, and aligned with overall system goals. This table illustrates examples of multidisciplinary trade-offs in drone design. Please take a moment to pause and review. To wrap up this session, we explored how to use models and simulations to perform requirement validation and make informed design trade-offs. By leveraging model-based design in Simulink, we demonstrated how to validate system-level requirements early in the development process, helping reduce risk, save time, and improve overall system performance. I hope this session gave you a clearer understanding of what requirements validation involves and how you can implement it effectively using Simulink. In the next session, we will focus on the requirements-based testing, exploring how to verify that system implementations meet their defined requirements through simulation and test cases. I look forward to your participation.